early, just a little bit, simply because we want to give everyone some time to join in, some padding time to get ready, get settled, and hopefully everything is working out as intended. So there we go. Hopefully it works. It appears to be. Okay. So this and this.
Holy.
Then so there we are. So hello there, Edu. Hi Esteban. Hi well, Joelle's obviously here. Hi Komi. Hi Silver. Hi.
Imagine Joelle not being here, but being in the chat.
Well, it might be an imposter. We do not know. And so, yes, today we will be discussing a paper you have written.
Yes, it is a paper on amortized analysis. Should I start the introduction actually?
I believe so. I think I'm going to pull up the paper you have written on screen just as a brief overview, and as I'm doing so, you can give the introduction.
Okay. Now?
Yes.
Okay, so hello everyone. I'm Joelle. I just wrote a paper on complexity analysis in computer science. And today I will be trying to present it in a less mathy and a less rigorous way.
Okay. Very good. Is that as far as the introduction goes?
I don't really know what else to say.
That's fine. That's good. Would you like to just already get started and get into the explanation?
Yeah.
Okay. I think that would be best done. I'm going to hide the paper for now. And we might as well get started.
Okay. So. Essentially, what we are going to do is compare algorithms. Algorithms are a sequence of instruction to solve a problem. It could be like saying that an algorithm to find a card in a deck of cards is taking the first card, turning. If it's not the card, just loop and do it again and again until you find the card. But there are multiple ways of doing the same thing. You can have multiple algorithms solving the same problems. Complexity analysis is a way of comparing these algorithms against one another. To do so, we will need at least a little bit of notation, which is what we will be starting with. If you have already done anything in complexity analysis, you might have heard of big O notation. I'm going to use N. Big O notation is a way of grouping functions together and talk not just about one specific function, but about a group of function. I just said twice the same thing. Oh. But it is useful to not lose ourselves in the little nitty-gritty details of our algorithms, because some algorithms can be much better than others, and this is enough to see these big differences. So, what is big O notation? I will not get into an exact definition, but for here it is enough to get an intuition to it. If I say, for example, big O of n, it means that I am including anything that is a linear function. For example, I can include n3 plus 2, 5n minus 5, and n itself. All that is in O of n. But, for example, n squared is not in O of n. It is in O of n squared, for example. O of n squared doesn't contain just the functions in O of n squared, it also contains everything that is below it. That is to say that O of n is a subset of O of n squared. Now, there is a slight issue with this, and that is that if I am talking about a function, for example, n, I could totally say that it is in O of n squared. But something doesn't feel very right with that. We kind of want to remove this, say that it is in O of n. To give more concreteness to this idea, we are going to introduce omega and theta. Omega is very similar to big O notation, except it is a lower bound instead of an upper bound. For example, if I take omega of, actually I'm going to take all that on the side. Oh, I just forgot to say, if anyone has any question, don't hesitate to ask. Anyway, so omega of g of x. Omega is essentially the opposite of big O notation. Instead of being an upper bound, it is a lower bound. That means that if we have omega of n squared, that means that we have all the functions that are in n squared, but we do not have all the functions that are lower than it. And if we take omega of n, we get all the functions that are above, as well as all the linear functions. So this time, omega of n squared is a subset of omega of n. Finally, the last notation we will need is theta. Essentially, when you say that a function is in theta of g of x, it's the same saying that it is both in big O of g of x and in omega of g of x. Essentially, this is no longer an upper or lower bound, it is a tight bound. I think that is it for this notation introduction. If anyone has any questions.
Apparently there was a bit of an audio bug happening. Let me
Nope.
investigate a bit. See what is happening. I cannot hear the bug. Actually, I suppose you are glitching out a bit.
I am?
Yes, but I don't know exactly why. So we're gonna power through it. Let's carry on.
Okay. So, that was the introduction to the notation. Now we are actually going to try and to use this notation on an example. Am I still glitching? Hello?
I'm checking.
Wait, hello?
Yep.
Oh, can you hear me?
Yes.
Okay. Yes, so we have here a little piece of code, of pseudocode. The goal with this of this algorithm is to take a list of values, like say A, B, C, and D, and we want to apply a permutation on these values to get, for example, this. To describe the exact permutation we want, we are going to also give it another list with where we want each value to go. For example, we are in computer science, so we are indexing from 0. For example, we want the value A. We want it to go to the place number 1. So we are going to give it a 1. The B is going to go to 0, so we give it a 0. The C stays where it is, and the D stays where it is. Essentially, what this algorithm does is it exploits the fact that there are some cycles in permutations. What I mean by that is that here, for example, A is going to be going at B's place, and B is going to be going at A's place. This is a cycle. It could also be a bigger cycle. For example, nope, that doesn't work. If we have this, maybe I should do it like this. If we have this list, now A is going to be going to the second place, so C. C is going to be going to first place, and B going to 0. This, once again, is a cycle. What our algorithm does is it checks for each index in the list of inputs it tries to solve a cycle. How does it do that? By swapping the value it is currently at with its destination. When we do this, for example, here we would end up with this. So what just happened is that A was moved to its destination at index 2. And it was swapped with C. We do the same over here, otherwise we are going to get some problems. And now we have swapped these two values. What is interesting with this is that it just puts one value at its right place, and we got another value from the same cycle. But now the cycle is just between these two. A is going to 1 and B is going to 0. So essentially, with each iteration of this while loop, we are shrinking a cycle by one value. And to be sure that we get all the values in the list, we do this for every value. Now, if we wanted to find the order of complexity of this algorithm, we could try to describe a function f that takes as input both lists and outputs the time the algorithm would take on these inputs. Sadly, there are two problems with this. First, it is not that feasible to describe this for every input, or at least it's probably easier to just look at the code. And also, it's not very useful because some inputs might have better time than others. Wait, no, I'm trying to...
Is everything okay? Do you need any help?
I am thinking. Also, it is this function done like this is a bit hard to compare to other functions. We have multiple inputs, and we don't really know how the function depends on these inputs. It's very hard to define. So instead, we are going to describe our function as taking a number as argument. This number is going to be the length of the input list, because we just have one restriction that these two have the same length. Otherwise, this wouldn't be a permutation of the input list. So n is the length of the two input lists. But that means that we can describe the time for every single input. We have to summarize the information. One way of doing so is by just considering for all the inputs with this same length, what is the worst time that the algorithm could take. Because now we have a pretty standard function. It takes a number as input, it gives a number as output, and we can write it for it like this, for example, compared to this function where it takes a list of values as inputs. Anyway, so what does this function look like? Wait. If we wanted to, rather, in what order, for now we are going to be in big O notation, what order is the input in? So we are trying to find a function, g, such that our time, our worst case time, is in this form. For example, if we can show that it is in O of n squared, we know that the function may be, the function f of n might be something along the lines of an squared plus bn plus c. So, in what order is it? If we take a look at our code again, we have a loop that is going to go over every index in the list. So that means that I'm going to remove these. That means that everything that is inside the loop will be repeated n times. Now the question becomes, what are we doing in this loop? How long is this? Well, as I said previously, this is trying to resolve a cycle in the list. So it is oh, I'm doing it right. If we have our input list and we have some cycle, for example, I don't know, this. No, that's not a good cycle. Let's do just this. The inner loop with the swaps is going to swap the A to its place. Then it's going to swap the B to its place, the C to its place, and finally the D. So it would seem like, worst case scenario, the inner loop will also do n operations. So we have n times n. Seems like our function might be in O of n squared. But something doesn't seem right, once again. When we get a full cycle like this, we first start the for loop, and on the first iteration, we solve this cycle with n steps, swapping everything to its right place. But that also means that every value that we saw in this cycle is now solved. It is in its right place. So that probably means that on the next iterations of the for loop, we are going to have less work to do. We can actually explain this a bit more. No. We can, I'm searching for a word. Yeah, we can investigate a bit more. Each time we do a swap in here, or rather two swaps, we are taking a value in the list and putting it at its right spot. But once a value is in its spot, we won't touch it again. We won't swap it. And we have only n values in the list. So we can only do over the whole life of the algorithm, we can only do n swaps because we only have n values to swap. We don't have n squared values in the list of length n. So that means that for our function representing the time the algorithm takes, we don't know exactly on which loops the swaps will be done, but we know that there will only be a maximum of n swaps. So our function is something like a constant, the time it takes to do one swap, times n. Then we have also the rest of the tidbits that are just constant time. And this is not just in O of n squared, it is in O of n. Now that we have this, well, this is good because it means that our algorithm is better than n squared, which was our initial result of the analysis. But it's not in n squared, it is in O of n. We still don't know if there's any lower bound, even lower bound that we could find. So we are going to try to show that it is also in omega of n. Because big O of n means that we are in n or below, and omega is we are in n or above. So if we are in both of them, then we are in theta of n, we are sure this is a tight bound. The easiest way to show that an algorithm is in omega of something is to give an example input on which the algorithm will take at least that much time. Because if we have g of x, the time our algorithm takes on the example input we give, it will be smaller or equal to the worst case. Because by definition, the worst case will always be worse than any other case. So, if we can find an example input which grows linearly, then we know that since f of x is necessarily greater or equal to g of x, then it will also be in omega of n, because omega is a lower bound. So it would be like saying that it would be similar to saying that n is smaller. I want to put an asterisk on this smaller. Smaller or equal to g of x. And so if we can show that this is true, necessarily f of x will also be greater or equal to n. Now, an example input on which it takes at least n operations is simply a list on which, as previously shown, we have a cycle containing every value. This list is going to have to swap at least once the A, the B, the C, etc. to get them to the right place. So every element will be part of a swap at some point to get it where it goes. So this means since we are doing at least n swaps, and this time not at most n swaps, it means that on this input, the time it will take is in omega of n. Since g of x is in omega of x, omega of n, this is n, not x. And since g of x is necessarily smaller or equal to f of x, f of n, we can finally conclude that f of n is indeed in omega of n. That is it for the first example. And could I please ask for a little break?
Yeah, absolutely. I think that would be fine. So I can just turn off the board, I imagine. Very simply. And for everyone watching right now so far, how you were feeling? How are you all? Because there is actually quite a fair bit of people watching. So, everyone, what do you think so far? In the meantime, as I turn off this, I can turn on the paper. I can have, as you can see right here, we have basically gone through the content of from the start to page 5. So the introduction being the introduction itself, and then a fair bit lower we have the notation, which has been discussed so far with the big O, the classic, but then also the omega and theta and what they mean. And then lower down, right here, the worst case analysis, permutation example. This is basically what we have covered so far. I am going to check just in case, because I don't know if no one is saying anything or if my YouTube glitched. Never mind, no one was saying anything. Okay, great. Great. Yes. So once again, if anyone is also having trouble following along, first of all, ask questions. That's precisely what it's here for. But at the same time, I would really recommend having the paper opened, simply because it makes it a fair bit easier to follow along with having the document that's all based on hand. Link is right there. You can go and view it. And if there happens to be someone with goobage amongst us, it's a bit of a rare thing, but I would like more and more people to have it, and eventually you'll be able to verify Joelle's paper. Do give it a read though first, to make sure that your verification is for a reason. But yes.
Okay. So, I think I'm ready to get back to it. So. Now there is the worst case analysis is quite useful. It is often very fast to find and gives relatively accurate results. But what if the worst case for a function is very rare? What if most of the time it's really fast, but maybe sometimes it's really slow? The worst case analysis, of course, is going to ignore that. It is a worst case analysis after all. What we could do instead is start talking about average case analysis. The average case analysis is essentially, instead of saying that f of n, where n is the length of the input, is the worst case, we are going to assume that our input variables behave according to some random distribution, and we can take the average time our function will take on these inputs for any specific n, of course. An example. If we have right here, we have a little piece of code to essentially compare two strings. A string is just a sequence of characters like A, B, C, D. And we want to compare it to another string like hello. Oh, kind of butchered the O. Our goal is to see, are the two input strings equal? In this case, for example, we can first immediately see that this string has 4 letters and this one has 5. So it's a bit useless to go on. We can just stop right now. We already know that these two are different. But if they have the same length, we have to start comparing each character in the string. Here, if we take hey and hey, our algorithm would start with the first character. Is it equal? Yes. So it goes on to the next. Is it equal? Yes. It goes on to the next. Is it equal? No. That means that somewhere in the string there's a different character. We can already stop. Here we were at the end of the string, but even if there was something else afterward, we can already stop. We know we're done. Now, what does the worst case analysis would have to say about this? We are, if we have inputs of length n, then the worst case is exactly like here. Everything is equal until the last character, for example. In that case, we have to loop over every character until we get to the end. So we do n operations, n comparisons. But what is that really a truly accurate thing to say? Because we can stop early in the comparison if the start of the strings are different. So we are going to try and apply the average case analysis on this algorithm. We are going to have to make a few assumptions. First of all, we are going to only consider cases where the strings are different, have the same length. Because if they have the same length, it's a bit trivial. It just immediately returns. So, when considering strings of the same length, we still have to describe what is the distribution, the random distribution of these strings. So we are going to say that, for example, if we have a string with 3 characters, each character is as likely to be any letter of the alphabet as any other. So essentially, it has 1 in 26 chance of being A, 1 in 26 of being B, 1 in 26 of being C, etc. And we do this for every letter in the string. This gives us a nice random distribution of strings. Now our algorithm. It is going to, the time it will take, I'm going to say g of x of n, the time it will take for one specific input is the time of the things at the start, just a constant time, like one comparison, and that's it. And then we have this loop. We are going to introduce a variable called k, which is going to be the number of characters, of equal characters at the start of both strings. And this loop is going to loop as many times as we have same characters at the start of the string, and it's going to do some constant of operation, so another constant. The only thing in this that depends on which input we choose is this k. So now the question becomes, what is the average k? What is the average number of similar characters at the start of a string? Actually, I'm going to keep that. If we have 2 strings, let's say with A, B, and C, and A prime, B prime, C prime. those are not the actual characters in the string. It's just to say that this is a string with 3 characters. And this is a string with 3 potentially different characters. Now, what is the chance of these 2 characters being the same? If we knew, for example, that this was the character A, we know that there is 1 in 26 chance of this character also being A, because every character in the alphabet is as likely as any other. But we can do the same reasoning with B, with C, with D, with any letter in here. We will always get 1 in 26. So actually, the likelihood that these 2 characters are the same is 1 in 26. Now, what is the chance that the 2 first characters are the same for both strings? We can apply the same reasoning to say that there is a 1 in 26 chance that B is equal to B prime. And we had 1 in 26 that A is equal to A prime. And since these are independent, the probability that both of them are equal is 1 in 26 times 1 in 26. So 1 in 26 over 2. If we apply the same reasoning for the third character, we would get 1 over 26 exponent 3. This is pretty general, actually. If we want to say the probability that the k first characters are... No, I'm not going to use k. The j first characters are equal, it is simply 1 over 26 exponent j. Now, this 1 in 26 over in 26 exponent j is the likelihood that at least that many characters are equal. For example, the 1 over 26 exponent 2 is the probability that these 2 are equal, but we don't say anything about C. What would be a bit more interesting is the probability that exactly these 2 characters are equal. To do so, we can simply take the probability that at least these 2 are equal and remove the probability that these 3 are equal. So, for example, we had 1 in 26 squared chance that both characters are the same, and we remove the probability that 3 of them are the same. Now that's good. We have the probability that the first j characters are equal, and we can do it with j instead of actual numbers. 1 over 26 j plus 1. This is useful because with this we can do a weighted average to get the actual average number of equal characters. What do I mean by that is saying that our average k is equal to the 1 times the probability of having only one character the same. So 1 in 26 minus 1 in 26 exponent 2. This is coming from here. But we also have a probability of having two characters the same. I'm going to have to move this. So we have a probability that two characters are the same, and this is 1 over 26 squared minus 1 over 26 cubed. Since we have only 3 characters here, the last probability is just 1 over 26 cubed, because we have no more possibilities to remove from this case. But you might realize that there are some similar sections in this. We could probably simplify. For example, here we have 1 over 26 squared, and here again. We have 2 times 1 over 26 squared minus 1 time 1 over 26 squared. And we have the same thing here with these two. We have 2 times this. No, we have 3 times this minus 2 times this. So if we expand, we actually get 1 over 26, the first one. Then we get 1 over 26 squared times 2 minus 1. This is just 1 over 26 squared. And the same here. We have 3 times this minus 2 times. So this just leaves us with 1. This is not just the case for strings of length 3. This is actually can be generalized to strings of any length. I'm going to shrink all of this up. Okay. Hello.
Either just ask, are the coefficients the amount of comparisons in each case?
Yeah. Yeah, exactly. So we are trying to get the average number of comparison. So it's if we have we do a weighted average of the number of comparison times its probability plus the number of comparisons times its probability, etc., until we get to the end of the string. Yes, so what we just wrote can actually be rewritten to be a geometric series. So 1 over 26 exponent I, and it goes from 1 all the way to n, if n is the length of our string. This can actually be simplified to remove the summation by doing this. I am not going to give the proof here. if you want to find it, you can search for sum of geometric series. But yeah, we can remove the summation symbol to get a nicer formula for our average k. And actually, this value, the only place where n appears is in he. As n grows large, this is going to get smaller and smaller, and it's going to go towards 0. Essentially, I'm doing a little bit of a limit as n goes to infinity. And so we end up with 1 over 1 minus 1 over 26. This is 1 over 25 over 26. And this is actually 26 over 25. This is a number, a constant number, towards which this function converges. That means that, and also, it is a little bit hard to see right here, but this function looks something like this. Oh, I should probably not have done that here. This, as n grows, looks like this, if this is our n and this is our average k, with 26 over 25 being like, hey, maybe. This actually means that our function will never go above this constant number. This is very good. It means that on average, our function will compare one number and maybe a bit more, like 2 sometimes. Since no matter what length of string we take, it will never go above this number. This actually means that our average case is going to be similar to our specific case, just with the average k. But since this only goes up to a constant number, all this will always be smaller or equal to a constant. A constant. Yep. This means that our function here, since it is always smaller than a constant, it is in O of a constant number. Because a function that just returns a number is in O of a constant number. And since our function is smaller or equal to this constant, it is in O of 1. O of 1 is actually the smallest possible order you could get. There's no like O of 0, for example. So if it is in O of 1, it is also in omega of 1. And so it is in theta of 1. That was the average case. So essentially, On average, we will only compare one, maybe sometimes two characters. But this is not often. So our function, maybe sometimes it will be slower, maybe sometimes it will have to compare a few more characters, but on average, it will take a constant time to execute. And I think that is it for the average case. Yeah, that is it for the example. Now, there is a problem with the average case. That is that I don't know about you, but I rarely type things like Wi-Fi. We assumed our inputs are going to be just random characters at each place. But sadly, language is not that easy. Some letters are more likely than others. Also, another problem, if we are considering the probability of seeing an H, it is probably more likely after a T than it is after a B. So it's not just that the probabilities aren't equal for all letters, it's that each letter is not independent from another. And if you actually manage to do the average case analysis for the English language, very good, very nice. Then someone tells you that your algorithm is actually going to be used in, I don't know, a compiler where you often have similar prefixes in names, and your average case analysis down the drain. So the two issues with the average case are that, one, it's hard to get. You have to know you have to be sure that your input acts according to a random distribution, and you have to know what this distribution is. And also, if your function is ever reused somewhere else, which is very common in computer science, your average case analysis might not hold anymore, since the distribution might change. Yep. An interesting way of solving this issue that I saw implemented in some sorting algorithms. There is an algorithm to sort list of values called quicksort. It is, as the name would imply, very quick, but only most of the time. In the worst case scenario, it could get pretty bad. Some people actually had the interesting idea to, before giving the input to the algorithm, they shuffled it themselves. This, in a way, guarantees that the input will act according to the shuffling they used, and so it will give them a specific distribution. So yeah, randomly shuffling a list of value is a valid optimization in some cases. I think this is it for the average case. And now the only thing left is the amortized case. So, the amortized case. amortized analysis is a way of, instead of talking about a single call to a function or an algorithm, we talk about a sequence of calls to algorithms. I don't have much room left. Might have to help. Yeah, amortized case. This is useful, for example, when the time a function takes to execute depends on previous calls to other functions. For example, we have here a FIFO queue called. It is called FIFO as in first in, first out. So, for example, you get in line to pay for your groceries. So you get in the line and you start doing stuff. Then someone gets behind you, another person, and then and that's adding values to the list. When we want to take out values from the list, it's from the front. So the first person in is the first person out. A way of implementing that is using two separate lists, one as input, the other as output. I am going to assume that we have a append function, which essentially just adds a value to the end of a list. So for example, if we have A, B, C, append would append with the value E, we do would just add our value to the list. We are going to, for this example, assume that this can be done in constant time. We also have something else, the opposite, to pop a value. This is essentially taking out a value from the list, from the end, and we return the value. So, now that we have all our tools, how is this FIFO queue working? Essentially, we have our inputs and our outputs. When adding things, we are just going to add them to the end of the input list using the append function. So for example, we are going to add A, B, C, D, and then at some point, we might want to extract a value, so dequeue a value. If we have something in our output list, great, we can just take it. Oh, what just happened? It's saying reconnecting. Okay. If we already have values in the output list, great, we can just pop the last value to take it out of the list. And that's the value we return. But if we have nothing, we take everything in the input and put it in the output in reverse order. With this, we can now, oh, why is it green? We can start popping values again. Since we put it in reverse order, the first one that was in is also the first one to get out. And we can just repeat this to extract more values, then maybe add some more, etc. What does the worst case analysis has to say about all that? To add a value to our data structure is pretty easy. All we are doing is appending a function to the end of the input. This is what this piece of code does. Since we assume that appending could be done in constant time, this whole function can be done in constant time. But what about the dequeue function? When we have values in our output list, it's pretty easy. Once again, we assume that we could pop values in constant times. But what if we have nothing in our output list? That means that when we have nothing, this is what this condition is for, we have to copy all the values from the input to the output. This is what we're doing here. This, since we are moving the values one by one, this takes about as many operations as the number of inputs we had in the input list. So the worst case analysis of this would be saying that enqueuing is in O of 1 and dequeuing is in O of n, if n is the number of values in the input list. But now, what if we wanted to look at a sequence of these instructions? I am to bring something. And for now, let's ignore this. But here is a little graph of the time our algorithms take to input and output value. In red, we input values, and in blue, we output values. The width, one rectangle is one operation. So for example, this is one in NQ, this is one NQ, this is one NQ, and this is one DQ, this is one DQ, this is one DQ. The width represents the time each one takes. So what is happening here is that we are adding 4 values, then we want to output something. But since we haven't outputted anything yet, our output list is empty. So we have to take all this sweet time to copy all the values back to the output list. And then we can finally output. And the next outputs are going to be fast because we already copied all the values. If we wanted to describe this in number, if we have k being the number of inputs we did before doing a big output, and we are going to say that C1 is the time it takes to do one input, one in queue, then doing all this work, I'm going to stop at the big input. if we have if we enqueue k values, that means that we are doing k times the enqueue function. So it's going to take the time of an enqueue function k times, plus this big time. This big time is coming from this loop mainly, and this loop depends on the number of previous enqueue operations, because the more values we add in the list, the longer it will take to copy them all to the output. So if we say that CA is the time one iteration of the loop takes, this will take k times CA plus the time to actually output the value. So a constant CB. But it is interesting to observe that these two Ks are the same. So what if instead we rewrote this as simply being K times C1 plus CA plus CB. Actually, I can hop. These two are exactly the same. Nothing has really changed. I just put since both of these are multiplied by k, I factorized the k to get to this and this. But this, in here, we had the cost of an enqueue operation followed by the cost of a dequeue operation. This looks awfully similar. We have two terms, and one of them is multiplied by k. This way of writing things would be like saying that each enqueue operation takes a bit more time because it is, in a way, paying up for the big dequeue that will follow. So, for example, this first enqueue actually takes this much time, but we already consider the time it will take when outputting. Same for this one, and this one, etc. And when we actually dequeue, in here we had a very long dequeue, but here it's almost as if we had just a constant factor. This is actually the amortized time. Essentially, we are saying that if the enqueue operation pays up for what it will cause later, then it will still be in constant time. It will be a bit longer, but it's still constant time. So it is in O of 1. But now, since everything has already been paid by all the enqueue operations, the outputs, the dequeues, are also in O of 1. So in amortized analysis, we could say that both, even though in the worst case, the dequeue operation could take a long while, when considering a sequence of these instructions, we can consider both of them as being in constant time. I think this is it.
All right. I have to say, like, very much. I didn't want to interrupt you, especially in the final segment, because arbitrage analysis was kind of the gem of the whole thing. But Randy has had a question for a bit of a while, which is where do they use this in? Which if I'm not mistaken, they asked during the FIFO explanations. So
Okay.
I do believe they were referring to FIFO, which even I can easily answer, which is it's more like a type of structure for storing things. So once again, the line at the grocery store, I think, would be a pretty decent example of a FIFO. The idea is that you have this kind of queue, and the first things that enter that queue are the first things that exit, except because of computer science, it imposes a certain restriction on how you handle it, which means that you in fact need two queues, and you need to copy from one of them to the other, the input to the output. But yes, it's just a structure in which the first things that enter are the first things that exit, hence the name. And the reason why it's so interesting, especially here in the case of arbitrage analysis, I love this graph, by the way, this graphic here, because that graphic really does convey the idea of arbitrage analysis beautifully. And so I think it was great.
Thank you. I will just say about the question from Randy Lewis. Here I was talking very generally because this data structure can be used anywhere, but I think one example could be requests on a website. A server receives requests one at a time, and it has to store them. And usually you want the first requests that were made to be resolved first. This would be an example of a FIFO queue.
Havayus asks a very on-point question. Does amortized analysis assume there is a large sequence of methods like n is large?
Not exactly. Amortized analysis actually says that you have to pay up in advance. So you could stop at any point in the execution. For example, we could stop at 2. I'm going to move that over here. If we stop at any point, for example, if we stop after 2 operations, the amortized cost should normally always be greater than or equal to the actual cost, because everything has to pay up in advance. That means that, for example, over here, we have a lot of things that are paying up in advance. And then when we use up all that, we have to still be at least equal. Doing something like this should not be possible in amortized analysis.
So effectively, it doesn't assume that there is a large amount. It doesn't assume that there is a large sequence of methods like n, but it does assume that there are multiple. As in, the reason why we're paying in advance is because we're effectively expecting eventually to have to pay the cost. So it assumes that you eventually have to pay the cost, but it doesn't require this kind of average, let's just say.
Yeah. If you could do the exact same drawing, just not do any DQ operations, and it would just mean that the amortized analysis will always be greater. It just wouldn't catch up, but there's no issue with that.
Okay. Well, there we have it. Any more questions before we leave it here? Then I just want to say, beautiful job, Joelle. I think it was tremendous. I think it worked out really good. Once again, for everyone watching, the paper is in fact available on the website. Link has been sent. So it assumes that the method call will pay less than or equal to the actual function for every case?
More than or equal. Oh, no, yeah. I just saw the new message. The true method call. Yeah. The true method call should always stay I am thinking. Yeah, I just said before that the amortized time should always be above the actual time. You could also see it as being that the actual time should always be below the amortized time.
There we go. That could be a bit unreadable, I imagine, actually, but I think this should, from perspective. So in when we're executing it, each operation takes some n amount of time, whereas in the amortized time we add like a padding in a way that is meant to account for the fact that eventually we'll need to pay the cost. So if we do it a amount of times, then n plus p will always be, actually hold on, greater or equal, there we go, then na.
That is it's
This only talks
it's
about the
great.
red zones, obviously.
Yeah.
So
yeah.
eventually you also have the method of getting it back, but the method of getting it back at most would just revert the piece. It doesn't have the capacity to move it back. Am I correct in this? The thing is, I'm asking in the form of a question, like you're the presenter here. I'm just trying to...
No, it's fine.
All right. Beautiful. Okay, I do believe then there don't appear to be any more questions. I also thank you, Edu, for listening actively. Very much appreciate that. And I think it has been pretty great. Alright then, I suppose we can end it here then. Once again, I will repeat myself. Paper available on the website for everyone to check out. Would recommend, go for it, go check it out. Give Joelle a verification. And for now, that'll be it. Thank you everyone so much for watching, and have a great day.